Very good morning. Any one of you, please let me know if today's slide is visible. Any one of you, please?
Yes, sir, it's visible.
Okay. I will start. Still a lot of time is here.
But his mirror image is visible.
Yeah, it is mirror image because I am using this one. But it should not have any problem because I am saving as a PDF file. Am I right? And sharing the video file also, video recording. Because the other thing I was having some problem, so it is fine. Okay, good morning. Let me start. So we were continuing with this one. So this is a Bessel function coefficient that we got it. As I said, no need to mug up these values. These will be provided. And we were having some interesting observations about this modulation index. If you recall, in my last lecture, we said that there are certain values of m where it is 0. So J0 is basically corresponds to the carrier. If you see the equation that we have here, so only carrier frequency will be 0. Obviously, there is no modulation, so no side frequencies will be there, which are represented by J1, J2, J3, J4, J5. Second thing we observed, though I have not put all the values, there are certain values of M, which we have put in the last table, in the last one, which is in the last lecture, that there are certain values like 2.4, 5.5, 8.65, where your M J0 is 0. That means there is no power in the carrier. All the power will be in the side frequencies. Okay. Now, continuing with that, there are certain other observations which I would like to continue here from this table and the equation. This was the equation of VFMT. That time I said we can neglect the VC, but if VC is there, it will be in the first one, and then it will be like a part of every term. So we get various terms, J0, J1M, and then J1M again, 2 pi FC plus 2 pi FMT and so on, which we have understood how this equation has come. Now here, as we see here, there are certain observations which I would like to continue here. Okay. So another observation is that if I have my modulation index less than 1, okay, your FM signal is composed of carrier with amplitude J0 into VC. Okay. If you see the previous equation, if you go back to the previous equation, it says J0 and VC multiplied by VC. Okay. So only the carrier is there if we see from this table. That is, but if it is less than 1, it will be a function of, sorry, I will write down this so avoid any confusion. I am writing M or MF, it is one and the same thing. Okay. Just for simplicity, I am using M here. But otherwise, we have to differentiate with the modulation index of the FM and AM. So it is J0M into VC. Okay. And it also consists of a single pair of side bands, 1 minute, with frequency so there will be many side frequencies will be there, but in this case, when MF is less than 1, I have only pair of side frequencies which are given by the frequencies omega C plus minus omega n, significant number of significant amplitude. That means big amplitude, which is given by J1 into M into VC. So this is called what we call a narrow band FM signal. So this is an important term which we call a narrow band FM signal. That means it is defined as MF is less than 1. So this we define as narrow band signal. Now, if you see here, if we see from this table, if I see less than 1, it consists of J0 or J1 and J2, but it is of very not significant amplitude because these decide my amplitude as we see here. 0.03 is very, very insignificant as compared to 1. So this is the first observation, and how with this we defined as narrow band FM signal. Otherwise, we call it as a wide band FM signal. Okay, so let me continue with this. And please note that I can also say that for wideband FM signal, MF, we can say it is greater than 1, or much greater than, even greater than 1. So that is how we define the narrow band and wideband signal. Then we come to the next conclusion. As your M increases, as we have seen, amplitude of first sideband, and these are all pair, okay, plus FM, FC plus FM and FC minus FM. So these are the all are pairs, also increases, okay, and amplitude of second sideband also become significant. So these are some of the observations which are quite obvious from this expression. So other thing is which we are seeing that is very important. Again, I put in a highlight. FM signal produces an infinite number of sideband, which I discussed last time. I concluded at this point, infinite number of sidebands. Okay, because they continue with that as we increase the this one. So I could also conclude from that means the bandwidth required to transmit FM signal is theoretically infinite. Okay, so it is an infinite bandwidth. Unlike in the case of a AM signal, where my bandwidth is just limited to twice of FM. But here, as you've seen here, number of sidebands will go on increasing as my modulation index is increasing. And this means I have an infinite number of sidebands and my information is contained in the sidebands. So that means theoretically, I need an infinite bandwidth for the transmission of the FM signal. So this is one of the disadvantages of the FM. But we have to overcome that. How we overcome that, we'll see later on. Okay. And as we increase the amplitude, M increases, number of side frequencies increases, and so on. Okay. And also I have seen, discussed that there are certain values like this one. So basically it indicates the reversal of phase. Whenever we talk about amplitude in negative value, that means I am getting the same voltage, say 5 volt, but it will be opposite in phase, that it will appear to be minus 5 volt. It will go below the 0. Okay, so this means like that. So I have an infinite number of sidebands and so on. But that depends upon the modulation index. Now let's do one example based on that. As I said, I always discuss my theory followed by an example. Suppose I have a signal, let's say your VMT is given to be some VM sine 2 pi 1000 t, and VCT, the carrier, is given to be 10 sine 2 pi. It is a very high frequency T. Okay. Now, what I have to determine? I have to determine how many side frequencies are there, and also the amplitudes of side frequencies. We have to find out, given that your modulation index is, let's say I take 1. Okay, if I take 1, I need to find what is the how many number of side frequencies and what are their amplitude. So for this carrier frequency and modulating frequency, my FM wave, how it will look, let's understand that. So we go for the solution. Okay. Now here, if you see here, it means your FM is equal to, it is around 1000 Hertz, and which is equal to 1 kilohertz. It means your FC is given to be 500 kilohertz because this is in Hertz. And this is my VC, which is given to be 10 volt. And given MF is equal to 1. Now from the table, as I said, we always prefer the table, though we have the graphical form or the equation. So this table is provided for M equal to 1. What we see here, if I see this table, I go back this one. I have one carrier and 3 pairs of side frequencies. Okay, 0.44, 0.11, and 0.02. So this is I'm looking for that too. So for this example, I have to look into this. So that means there will be one carrier and 3 pairs of the side frequencies are there. Okay. So from this table, which is on slide 1, for M equal to 1, which if I see, it will give me a carrier and 3 side frequencies. 3 side frequencies pairs. Okay. So what are those side frequencies? These side frequencies, so I will get a FC. I will get FC plus FM, FC minus FM, FC plus twice of FM, FC minus twice of FM, FC plus thrice of FM, and FC minus thrice of FM. So I will get something like this. And their amplitudes, so these are the side frequencies, which means I will get the frequencies of, so I will get 500 kilohertz. And here I get 500 plus 1. That means 501, 499, 502, 498, 503, 497. So these are the 7 frequencies I will get. Carrier, the original frequency, and 3 pairs of the side frequencies. And what about their amplitude? So this we found out, number of side frequencies. So 3 pairs of the side frequencies. And what about the amplitudes? Now from the amplitude point of view, amplitude of carrier is J0 into VC. So J0 into VC, and amplitude of first pair of side frequencies is J1 into VC. Amplitude of second pair of side frequencies, J2 into VC. And amplitude of third pair of side frequencies is J3 into VC. So J0 was how much? 0.77 into 10 volt. So that becomes 7.7 volt. This becomes, if I see from the table, 0.44 into 10 volt, 4.4 volt. And if you see the J2, what was the J2 value and J3? I'll go back to this table. That's why I put in the first slide. 0.77, 0.44, 0.11, and 0.02. Okay, so 0.77, 0.44, 0.11, 0.02. So this is, again, I look for that. It is 0.11 into 10 volt. So that gives me 1.1 volt. And this is 0.02 into 10 volts. And that gives me 0.2 volt. So my FM signal will look like this. See, just like we have the case of FM. So I have got 500, 501, 502, 503. That is my frequency in kilohertz. Okay. And also I get 3 here, which is 499, 498, and 497. Okay, as we see here. And their amplitudes will be like this. So 500, I got an amplitude of 7.7 volt, and this I got an amplitude of 4.4 volt. Here also 4.4 volt. Then this another amplitude of 1.1 volt and 0.2 volt. Again here 1.1 volt and 0.2 volt. So just like in the case of M, so here my bandwidth is from 497 to 503 6 kilohertz. But theoretically it is infinite. But in this case, because we go for that, so theoretically it is infinite. So this becomes my bandwidth of this particular signal, which is turns out to be 503 minus 497. That means 6 kilohertz is the bandwidth to transmit this FM signal. Okay, so that is how we talk about this thing. And as I said, when we talk about this one here also, it is also called, I'll put it here, MF is called the low index case. So this becomes my low index. And this is called the high index, modulation index, high index case. And this is low index case. So we also talks about low index and high index, or narrow band and wide band FM. Okay. Now moving further, let's talk about in terms of the power also, because finally what we are transmitting is the power. Now, before we go for the power, let's understand one more thing. See, as per this Bessel function, which is an approximation, as you see, it is a factorial of n and some expression, and you go on continuing like that. So it does not give the true bandwidth. It gives you a yes, that the bandwidth is going to be significant and so on, but it is not a true bandwidth. So how to measure the true bandwidth? Okay, so that is given by what we call the Carson's rule. Okay. Sorry, this is Bessel function gives you the exact bandwidth, because we are using the exact Bessel function. But I need to approximate also. And for approximation, I don't need to refer to this graph of the Bessel function or the table of this method Bessel function, or for the equation of the Bessel function. Okay, so I need to approximate. Sometimes we do the calculations, and every time we can't have the Bessel function table or these things, which gives me the true bandwidth. So for approximate bandwidth, we have what we call a Carson's rule. This is very important rule. Carson's rule for FM bandwidth. Okay. Now, what is this one? So it basically gives me an idea of approximate bandwidth, not the exact bandwidth. Exact bandwidth is obtained using this one. So as we have seen earlier, why it is not writing? So exact bandwidth obtained using Bessel function as discussed above. Okay. Okay. Now, Carson rule will give me the approximate bandwidth. So Carson rule gives me the, I just write down for you, approximates the bandwidth which is necessary to transmit the FM signal as twice the sum of peak frequency deviation, which we have discussed. Peak frequency deviation is given by delta, which is in hertz, and maximum modulating or message frequency FM. Okay. Now, if you see here, what it means, that is mathematically, I can say mathematically bandwidth of FM signal, FM bandwidth, so which I denote as BFM. Okay. Okay. So it is given by twice of delta plus FM. Recall that mathematically for AM was twice of FM. But here this is in frequency deviation. So this is also in hertz. So if I recall for AM, bandwidth of AM was twice of FM, the maximum value. But here, maximum of this one. Okay, so that is what we have understood for the AM. But here it is given by this one. So that means I can approximate. So this is my, what we call the Carson rule. It is an approximation. So if I know the peak frequency deviation and the modulating frequency, this becomes my bandwidth as per this one. But for the true one, I have to go the way which we have described in our problem in this case. So again here, so this is the bandwidth of FM, which is, as I said, twice of delta plus FM. Now here we have two cases. When I have one, okay, and modulation index, if you recall how it was given by that one, that is, if you recall that MF is equal to which we have delta over FM. Okay, that is how we have defined, which is so it implies that I will put it like this. For MFF less than 1, or I could say FM is greater than delta. Since we have seen your MF is nothing, I should write down like this, delta over FM. Okay. So if MF is less than 1 or delta is, FM is much, much greater than the delta, we defined the bandwidth of narrow band FM. Okay. So this is an approximation. So we write like this. So please note that because this is an approximation, we write it like this. It is the twice the sum and is approximately. Okay. So I write it clearly here. Okay. So we write it as an approximation here. Okay. It is not true bandwidth, just to go for that. So here also I put it in the in this way. That was my Carson's rule. Okay. So I defined bandwidth of a narrowband FM signal, which we have. Why it is not writing? Is given as twice of. When there is some problem in my writing today. I don't know what is the problem. So it is given as bandwidth of a narrow band FM signal is twice of FM in hertz. So that is what we got is. So this is the bandwidth of narrow band FM. That means MF is less than 1. And for MF is greater than 1, which we defined as the wideband. Okay. 1 minute. Or delta is greater than FM. Again, the same equation, that is MF is equal to delta over FM. Okay. So what we get here is, for this expression, your bandwidth of wideband FM signal. So bandwidth of wideband FM signal is nearly equal to 2 delta. Again, it is in hertz because delta is greater than FM, so I can neglect that. So that gives me the bandwidth of the wideband FM signal, straightforward. FM signal, which we defined as MF is much, much greater than 1. So this is the two definitions that we got it. If you see here, this is the one, approximate this one. So both these expressions are also approximate here. So narrow band and wide band, which we have defined in this slide, as we have discussed in the previous case, a narrow band and a wide band FM signal. So this is very important to understand what is narrow band and wide band. Also, I forgot to tell you, there is one interesting thing that when we talk about the AM signal, it has the bandwidth of twice FM. Okay. So I can say for MF less than equal to 1, FM behaves like AM. Like AM. This I went back to the previous slide. That means carrier and two side frequencies. Okay. So this is also another observation that if my modulation index is less than 1, your FM behaves like AM. As you see here, if less than 1, much less than 1, so that means it could be 0.7, 0.8, though I have not put all the values. We'll find one carrier and two pair of side frequencies of significant amplitude. I can neglect 0.03 and 0.04 or something like that. So that is not significant amplitude. But as I said last time, if I see this one for 0.25, exactly it is the AM, because it is having one carrier and the one pair of the side frequencies corresponding to J1. That means FC plus FM and FC minus FM. But in general, because this table is not complete, I have taken only few values. If I have modulation index much less than 1, FM behaves like an AM signal from the frequencies bandwidth point of view. But their amplitudes will be different. Okay. Now let's take another example or understand this, what we have learned. Let's say, so I take another example. Suppose I take I got a FM modulator. That means it generates a FM signal. It operates at carrier frequency of 500 kilohertz. So FC is given to me having peak amplitude of 1 volt. Amplitude of 1 volt. And this has a modulating frequency, which is my message frequency. So I'm not using the word message again, because modulating is what we normally use, of let's say 10 kilohertz. It modulates it with a peak frequency deviation of 10 kilohertz. Okay. So find what is our aim? Find actual bandwidth. I will change the pen. Just give me 1 minute. So I find the actual. So I change the pen because there is some friction there in the previous pen. Some static charges get developed on my iPad. So yes, I think it works. It should work fine. So I find the actual bandwidth. Actual means exit bandwidth using a Bessel function. Obviously, you need a Bessel function for that. Exit. And so obviously I need a Bessel function for that. And then the approximate bandwidth. And for that, I am giving the hint using Carson rule. Though it is not specified, but I'm telling you right now, when you have to find the exit and all those things. So actual bandwidth and approximate bandwidth, which we normally use Bessel function and Carson rule. So for this solution, if I go for the actual bandwidth, your MF is nothing. It is, I need to find MF for Bessel function. So this is given to be 10 kilohertz, and this is given to be modulating frequency of 10 kilohertz. So both are given to be 10 kilohertz. So it gives me the modulation index is 1. Okay. So this is the what this is given to be my delta, and this is also given to be my FM. So it turns out to be 1. And if I see using a Bessel function table for M equal to 1 or MF equal to 1, what we get here is your bandwidth is basically, if you see this Bessel function, it is the same case as I have taken here in this example, M equal to 1. That means the carrier and the 3 side frequencies. So I get a carrier, FC, and 3 pairs of side frequencies. And that is given by, so one is FM, twice FM, and thrice FM. These are the 3 pairs of the side frequencies. Or I would say, don't write like this, to avoid any confusion, which is given as FC plus minus FM, FC plus minus twice of FM, and FC plus minus thrice of FM. Okay. So here it will be, my bandwidth will be twice of thrice of FM. That means 6 FM. And this is given to be 6 into 10 kilohertz, which is the 60 kilohertz. So 60 kilohertz is the exit bandwidth. Okay. Now, for the approximate bandwidth, if I go, so if I calculate the approximate bandwidth using Carson rules, what is that? It is given as bandwidth of FM is twice of delta plus FM. So in this case, it turns out to be twice of. So I'm using the approximate sign, 10 kilohertz plus 10 kilohertz. So in this case, it turns out to be 40 kilohertz. So what we conclude here, we can conclude something that there is a significant decrease. I am speaking also and writing so that it will be helpful to refer to these notes only for your examination in bandwidth determined from Bessel function and Carson's rule. Okay. And normally, what we do, if I have got a FM system having MF less than, let's see, equal to 5, would have a narrower bandwidth and thus poorer performance, okay? Because then my approximation will not be very much different if it is designed using Carson rule, as you've seen here. So up to nearly FM, MF is less than 6, FM or MF is less than 6 in certain books, you will find that your FM system will have a narrower bandwidth, as we have seen here, using the Carson rule, and a poorer performance, quite significant decrease. Okay, but this significant decrease is found only in the lower MF or lower values of the modulation index. So what is the golden rule here? The golden rule says that Carson's rule should be applied as an approximation to the actual, or whatever you call exact bandwidth, when MF is greater than 5. That's the important thing. Now, this was about the narrow band FM signal, low modulation index, wide band FM signal, or what we call the this one, which is basically this one. Now, let's take our example of how to calculate the power. Once you have understood this one, let's take one example how to calculate the power. So this is the new example I'm taking, which is from the power point of view. Like in the case of AM, what we have seen that maximum power is transmitted in the carrier, okay, and the power transmitted in the sideband is not that high, okay, even for the 100% modulation. Here also, let's see how my power is calculated and so on. So this is something what we'll do through an example. So this is a new topic. So basically, it is for the determination of. So I will take through this as an example of power of carrier and side frequencies in FM. So let's take one example. It will be better to take directly an example. I take the modulation index as 0.5 for simplicity, okay, and for a 5 kilowatt FM transmitter. Okay, so if I want to transmit a 5 kilowatt using FM transmitter and my modulation is index is 5, how much power will be carrier and how much in the side frequencies? Okay, if you recall in the AM, we have seen that the most of the power, if I take the modulation index as 1, is in the carrier. And the power in the side frequencies is not of that significant. Well, it is very less as compared. So most of the carrier power is wasted in the carrier because carrier doesn't carry any information. It is the side frequencies that are carrying the information. So here, let's see what will happen. Okay, it depends upon the modulation index. So let's say my example is FM is equal to 0.5 and this one. And we do the true calculation. Okay. So if I have to go for that one, using Bessel function table for MF equal to 0.5, okay. I have three frequencies, which is J0 is 0.94, J1 is 0.24, and J2 is also there, but not significant, but we calculate the true power 0.03. Okay. Now, because I have to find, what is the power in the carrier and what is the power in the side frequencies when I transmit the FM signal through FM transmitter, which is carrying a power of 5 kilowatt. Okay. So from Bessel function, I found that there are significant of this one. Okay. So I got one carrier. So I got carrier and two pairs of the side frequencies. Obviously, one is more significant, but we calculate exactly. So all the three are there. Now this is, we got it. And also we have seen, because this is the voltage we are talking about so far. So I say, let's go back to this one. Since power is proportional to the square of voltage. Okay, so far we were dealing in the, but we normally discuss in terms of voltage and current, but what we actually transmit is power. So far what we were discussing was in terms of the voltage. Okay, because we know that P is equal to V square by R. Okay, R is some load, which could be the load of the receiver or something like that. Okay, so with this equation, I can say your carrier power is equal to 0.94 square into 5 kilowatt. Okay, that's my VC, okay, which is given to be 5 kilowatt. Okay, so carrier power becomes this much, which is 4.418 kilowatt if I calculate. Okay, so that is the exact value which I have with me also. So that becomes my carrier power. And power of first pair of side frequencies, it is a pair. Frequency means twice two numbers. Okay, so it will be given by 0.24 square, okay, into 5 kilowatt into 2. This 2 has come because of I have two pairs of the side frequencies. Okay, and here if I calculate, it turns out to be exactly 0.576 kilowatt. So that is the power in the two side frequencies. In one it is 0.288 and in the both the one it is 0.576. And finally, power of second pair of side frequencies, which is pair of means two numbers again, it is given as 0.03 square into 5 kilowatt into 2. Again, as I said, because we have two pair, so I'm multiplying by 2. Carrier is only 1. So if I calculate this, it turns out to be 0.009. So it is not a significant power as compared to the carrier and the first pair of the side frequencies. So these are the power in terms of the power. So far we were working in terms of the voltage, but finally, as I said, in the transmission system, we never transmit voltage or current, but we transmit the power. So this is the, let's see the total power. So my total power, if I see, it is 4.418 plus 0.576 plus 0.009. That is 5.003 kilowatt, which is nearly 5 kilowatt. So here power won't change. That is the same power gets transmitted. So with this example, as I told you, I wish to inform you that uh, the total power is equal to the unmodulated carrier power. That is an important conclusion we got it. In FM, your total power is equal to unmodulated carrier power. Very important. And it is so because the amplitude of carrier doesn't change in frequency modulation. Okay, because amplitude doesn't change, so that means the voltage doesn't change. That means the power doesn't change in the case of FM. In the case of AM, we have seen that the amplitude is changing. It is giving like a fish type of the structure of fame, this one. So my power was changing, okay, depending upon the modulation index. Here what you see, my number of frequencies will change. Okay, how many frequencies are generated? There I know only the two side frequencies are generated because the frequency is changing in the FM and not this one. So this is something about the power and all those things. Okay. Let's hmm. So this was more about the frequency modulation as we have discussed. Let me see if and then we'll move to the before we move to the FM PM, the phase modulation. Let's talk about what we called it our FM radio. Now FM radio. Let's talk about our commercial FM radio. This is an application, as you have seen here. The application of FM is your mostly the FM broadcasting system. So let's talk about the commercial FM radio, which we normally hear, still hear what we call as a So if you see here, FM radio frequencies, as we have seen here, it is something 88 to 108 megahertz. Okay, like your radio Mirchi is 98.3 megahertz. So how we divide our stations here, okay, how we divide our stations. So range of FM frequencies is 88 to 108 megahertz. So basically what we have seen in the case of AM radio, let me bring the AM radio also back into the picture here, AM radio broadcast system. Okay, so basically because I have not talked about the AM broadcasting system. So first we'll discuss about the AM broadcast system because I forgot that time somehow, and it is important. AM. So I'm writing specifically here, amplitude modulation. So this is something I forgot. So AM broadcasting system, if you recall, it was having a frequencies from 535 to 1605 kilohertz. That is, my frequencies are from in this one, all my radio stations. Okay. So here, as I said, if I modulate the carrier with a, so if you see here, what we transmit a audio signal. So audio frequency range, whether it is an orchestra or it is a flute or it is something like that. When it was introduced, that time it was limited to 5 kilohertz, which is my FM. Okay. So if I'm modulating the carrier with, let me write, with the 5 kilohertz message signal, okay, required a bandwidth of twice of FM. That means twice into 5 kilohertz by 10 kilohertz. So basically what we transmit, a audio frequency there, audio signals there. We never transmit broad video in the this one, only the write it clear. Okay, so here my audio frequency was limited to 5 kilohertz, so I got it 10 kilohertz. So that means the lowest channel or the first channel will have frequency of 540 kilohertz. Why? Because I have various stations. Now this is my station number 1, okay, station 1, okay, or channel 1, as we normally say, channel 1. So this is 540 kilohertz, because I need a bandwidth of 5 kilohertz here and 5 kilohertz here. So that becomes my 535 and 545 kilohertz. Okay, so this is FM. This is FM. So my first station is tuned to 540 kilohertz, which has a lower side frequency of 535 and upper side frequency of 545. Okay. Then the next station will be at what frequency? It will be having a frequency which is extending up to 550. Okay. And it will having another one 555. Okay. So this is my channel 2. This is my channel 1. Okay. And the third one will be having a 560 and 565. Again, this is FM. And that means I need a transmission bandwidth of twice of FM, which is 10 kilohertz. Okay. So that means I will have so many stations, station number 1, station number 2, and then we'll have station number 3. Let's say this is, and then we have many stations tuned to that. And the last station, as I said, is 1605. So the last station will be at 1600 because it needs a bandwidth of 1605. And this is a 1595 kilohertz. So this is again FM and this is again FM. So this becomes my last station, last channel. So I could have so many channels. If you count, from 540, 550, 560, and so on, I have various frequencies. So therefore, we have 107 channels, or I would say AM radio stations at 540, 550, 560, and all the way to 1600 kilohertz. Okay, each having bandwidth of 10 kilohertz. Okay, that is 535 to 545, 545 to 555, and so on. So this is the so many broadcasting stations we could have. Now, if you recall, we don't have so many broadcasting system like we tune our radio to one of these channels. Let's say Vivid Bharati, it is having one frequency. Let's say one of the frequencies could be, I could not recall, 1100 megahertz or so. So here, what is happens here? That time when AM was there, if your parents or grandparents may be recalling, like in 1983 when the World Cup commentary was going on, उस time TV नहीं थे, and India was going to win the World Cup. Uस time even the semi-conductor devices were not there. So people used to use, the radios were very big, used to use that valves and so on. And then if you recall, it takes so much time to heat it up. That means I wanted to know what has exactly happened, but it took time to switch on this thing. And also sometimes the stations get overlapped because you are just having a 10 kilohertz bandwidth. So as you've seen, if slightly my modulation index is increased or something like that, there is a over modulation or splattering. Okay. Then my channel overlaps into the other one. So the two stations combine with each other. And I may not have, sometimes the cricket commentary is coming in one, and another farmer is talking about the farming techniques, so that used to get the mixed up. And this time that this phenomena was used to be used by various stand-up comedians that time, that they mix the two commentaries, like one how the farming techniques, another one is talking about the cricket commentary and all those things. So this is like a inter-channel interference used to be there, because uh, so many broadcast stations are there. Yes, I agree. There are 107 broadcast stations are there, but they are closely spaced, just at 10 kilohertz. So to avoid that in FM system, as I said, we wanted to avoid this over modulation, which we have discussed, or splattering in the case of FM. So we'll talk about our now commercial FM radio broadcasting system. Now in commercial FM radio broadcasting system, as I say, now I clearly space here frequency modulation, so I back into the FM. What they did, which is basically from 88 to 108 megahertz. Okay, so the frequencies are large, so bandwidth is also large and something like that. So here it was defined that each station, what we have learned from that one, or channel, is allowed plus minus 75 kilohertz frequency deviation, which we have learned. Okay, and or 150 kilohertz carrier swing, which we have learned, which is twice of the frequency deviation. Okay, as discussed earlier. Okay, so that is, we have discussed these terms, frequency deviation or something like that. So we here be assigned a plus minus 75 kilohertz of frequency deviation, or a carrier swing of 150 kilohertz. Okay, so here what will happen here? Then also, to avoid what we have seen in the case of AM, because FM is a superior system. Why? Because something what we found problems there. Here also an extra guard band, a 25 kilohertz guard band. What is this guard band? I will just explain to you. is then added above and below carrier frequency. That means total bandwidth of one station is 200 kilohertz. How? So this is my station, like say channel 1 or station 1. So I allow 75 kilohertz here and 75 kilohertz here, plus additional 25 kilohertz and 25 kilohertz here, 1 minute. So this is my frequency deviation of plus minus 75 kilohertz, and if I is my guard band, 25 kilohertz on either side. Frequency deviation of 75 kilohertz on either side. That means my each station requires a bandwidth of 200 kilohertz. So if I add up these all these, it turns out to be total of 200 kilohertz. If you recall, in the FM system, my total bandwidth was required as 75 or 10 kilohertz. So I just write down. In AM, bandwidth of each station was 10 kilohertz. And now here it is almost 200 kilohertz. That means 20 times. So here my station becomes like this. So I will have many stations, something like this. So here in my FM, as I seen here, I will have various stations, something like this. Let's draw it again. This, and this. So this is first station, which requires 200 kilohertz. This is the next station, which requires 200 kilohertz. So this is my carrier 1 or station 1 or channel 1. And this is my number 2. This is minus 75 kilohertz. This is plus 75 kilohertz. Again minus 75 kilohertz. I write it clearly. Minus 75 plus 75 minus 75 plus 75 kilohertz. And this is what we call the 25 kilohertz guard band. Okay, my 5 is not coming nicely. Let's mark it as like this. 25, 75, 75. So all these are guard bands, which I have shown in the shaded one. So this is my bandwidth required for the each channel. Now, if you see here, as we see here, because my frequencies are from 88 to 108 megahertz, let's make this story complete. So how many channels are there? So if I go by that one, because 100 kilohertz here and 100 kilohertz there. So my FM radio will look like this. I have various stations. I start with this one. So there is a garment of this one. There is another garment. There is another garment. And then there is another garment, another garment. And it will continue. And we'll finally have another garment. So my first frequency will be 88.1. Next will be 88.3. Next will be 88.5. All these kilohertz, because 100 here, 100 here. So it starts from 88 and it ends with 108 megahertz. So this is all in megahertz, sorry. So my first station will be tuned at 88.1 megahertz. Next station will be tuned at 88.3 megahertz. Each station having a bandwidth of 200 megahertz, 100 megahertz on the either side, 75 kilohertz frequency deviation, 25 kilohertz is the guard band for each station. Okay. And the last band will be, because it is 108 megahertz, so the last frequency will be 107.9. So that becomes my 108 here. Again, 100 megahertz here and 100 megahertz on this side. So this becomes my total number of stations. So basically there are about, you can calculate how many stations will be there. 100 stations will be there totally. Okay. So if we calculate by this one, so there will be total of 100 stations. Okay. So there will be total of 100 stations. In case of FM, AM, it was 107 station. Each station was having a bandwidth of 10 kilohertz. Now here we have got 100 stations, 88.1, 88.3, 88.5 and 279. Each station bandwidth of 200 kilohertz of plus minus 100 kilohertz. That is of 200 kilohertz. In AM, if you recall, 107 station. Each station bandwidth of plus minus 5 kilohertz and 10 kilohertz. So obviously the bandwidth is high and the same audio signals I'm transmitting, audio signals, there is a less chance of interference. So it becomes less noisier. It becomes very less noisy and so on. But because these are high frequencies, megahertz as compared to kilohertz, so here the power can't be generated like at the lower frequencies. As you move towards high frequencies, the power generation becomes very difficult. So here we, like in FM, I have a different radiometry. Let's say I brought a radiometry station, which is 98.3. Okay, 98.3, it comes like that. That means it is having a bandwidth of from 98.2 to 98.4, and it is transmitting. So they bought the frequency 98.3. But because of less power generated at these frequencies, they can't transmit to the large distances. Unlike AM, which is used to be at lower frequencies. So the same broadcast which is in Delhi used to be there in Chennai also, Vivid Bharati. And here also, they bought the frequency, radiometry, but they transmit differently. For Ahmedabad, it is a different FM radio. For Mumbai, it is different. For Delhi, it is different. But they bought the frequency. Like Uber has bought a certain number which is the same. You have to just prefix the STD code. So here it is about all the AM radio, AM transmission, AM bandwidth, AM various parameters, and then FM radio, FM transmitters, FM, all those things. Now in the next lecture, we'll move to the phase modulation. As I said, both are part of the angle modulation. But just the way we define the both are part of the angle modulation, both go in the same way. We'll talk about various parameters also in the phase modulation, which we'll discuss in the next lecture. So we completed AM part, FM part, introductory part. So only thing is remaining is PM, which is just an extension of AM. And then we'll talk about the noise and that becomes the part of your analog communication, which will be the syllabus of the examination or the mid-sem, which is scheduled on something like 9th or so, but that we'll discuss slightly later on. Yes, so this is all about the any query. I don't see any checkbox. Any query before I stop this? Okay, no queries. So I end the call, stop recording, and share the recording and my slides with you. So we'll start with the phase modulation in the next class.